Hello, in this video we're going to talk about a key fluid dynamics concept, and that is Bernoulli's equation or Bernoulli's principle. And this is a very simple concept, yet it is extremely useful. So it basically says that along a streamline between any 2 points of fluid flow, and we'll get into the the limitations or the constrictions of this problem, but it basically says that the pressure plus 1/2 rho, so the density, times the velocity squared, plus rho, density, times gravity, times the height is constant. So, where P equals pressure, rho equals density, V is the velocity, H is the elevation, and G is the gravitational acceleration. And usually you'll see this drawn out like this, because usually you're analyzing this between 2 points. So you can say the pressure at point 1 plus the 1/2 rho V1 squared plus the density times gravity times the height equals this. And of course, if you analyze both sides, they're in units of pascals, because obviously pressure, that's pascals, rho GH, that is pressure, and then this is the dynamic pressure right here. So it's all in the units of pascals on both sides. So kind of the constrictions of this problem would be points, the limitations, or the assumptions, I guess you could say. Points 1 and 2 are on a streamline. So what that's basically saying, so if we have, like, just say like a basic pipe here, you know, point 1 and then point 2, obviously these can be tracked along a streamline. But let's say we had like a bucket of water here, and then like a bucket of water here, and like point 1 is here, and then point 2 is over here. There's no streamline that you can make to connect those points. The fluid has to be a constant. The density, so the density can't be changing, and the flow is steady. And the big one that we're negating here is no friction. That's another important thing that we are negating here. So those seem to be pretty heavy assumptions, but for a lot of applications, this is good to use. So in this problem, we have a couple requirements. So in which we're going to use the Bernoulli's principle to solve this problem. So we have a fire truck here at the bottom of this building, and it needs to bring up water 381 meters in the air to the top floor of the Empire State Building. And our requirement is the mass flow rate of the water needs to be 78.3 kilograms per second, and the diameter of this hose at that point is 5 centimeters. That's to be the diameter where the water is coming out. So we want to solve what is the pressure needed in this tank to bring the water up to this height. Now obviously this is kind of an unrealistic problem, but for the sake of using Bernoulli's principle, we can use it. So let's write out our equation and then start canceling things we don't need and then figuring out the things we do need. So this is our state 1 here, and this is state 2. So this is our streamline here, okay? So this is our control volume, you could say. So all of this water can be tracked along a streamline from here to all the way to there, okay? So P1 plus 1/2 rho V1 squared plus rho GH1 equals P2 plus 1/2 rho V2 squared plus rho GH2. And hopefully I'm not making too many assumptions with like continuity equation and stuff like that, but we'll figure it out here. So the pressure at 1 is what we're trying to solve, okay? So that's what we're trying to solve, the pressure at point 1. Now, the velocity at point 1, I'm going to say is 0, because it's in a big tank where it basically starts at 0. It has no, it has no kinetic energy. It's not moving forward at the point 1. It's like at the bottom of the tank. We're not worried about what's upcoming here. We're not worried about here. We want to worry about the water at the bottom of the tank, which basically has a velocity of 0. So this whole thing can be canceled out. And also, we are basically saying that the difference in height between the top floor of this building and then where the water is, point 1, is 0. So we're going to say H1 is 0. So that would be called our datum. So we're picking that as our datum. It needs to get at 381 meters from the datum to the top floor. Now the pressure at 2, we're going to say is the normal atmospheric pressure. So we can say P2 equals 101,325 pascals. Okay? Okay, now we need to solve for V2. So we know the diameter of the pipe or the hose, and we know the mass flow rate. So we can use our equations that says mass flow rate equals rho VA. So, and we know density of water, we'll say, is 997 kilograms per meter cubed. So we're trying to find the velocity. So this would be V2 times A, which would be pi times R. So I'm going to say, actually, this should be the radius. Radius equals 5 centimeters. So 0.05 meters squared equals our mass flow rate of 78.3 kilograms per second. Solving for V2, that equals 10 meters per second. Water flow, so V2 equals 10 meters meters per second. Density 997 kilograms per meter cubed. P2 101,000. Okay, moving on to the next term here. Density, we have that. Gravity, we know what that is. And H2 is our 381 meters. Okay, let's solve it here. So P1 equals 101,325 pascals plus 1/2 rho, which would be 997 kilograms per meter cubed, times our velocity, which would be 10 meters per second, all that squared, plus our density, 997 kilograms per meter cubed, times gravity, which would be 9.81 meters per second squared, times our height, 381 meters. And then solving this, we get 3,877,572.17 pascals. So that was what the pressure of the tank would need to be to get this water up. That's a lot of pressure, so we can solve that for barometric pressure, so that'd be 38.78 bar. But let's say I also want to solve, like, what would we're just also going to continue this problem. So there's a pressure of the tank. But like, how deep in the ocean is this pressure? So at what point in the ocean do we reach that pressure that is reached in this tank, or theoretical tank? So we can set P equals rho GH, so 3,877,572.17 pascals equals, and we'll say our density is 997 kilograms per meter cubed, times gravity, meters per second squared, times our height, which is what we're trying to find, and that height would be about 396.5 meters below sea level, which is pretty deep. That's like pretty deep. So I don't know how deep that is in feet, but it kind of just shows how much pressure you would need. And that's because water is very heavy. So that's just a problem using Bernoulli's principle.